Good morning, it's me, Mr. Truman, back again for another lesson in geometry. Today we're going to be looking at isosceles triangles and equilateral triangles. So we're going to look at each of the properties that these two triangles possess and then how we're going to use that towards solving problems. So our first one we're going to look at today is the isosceles, and the word isosceles means a triangle that has two sides congruent. So when we look at a triangle and we see that they have two sides that are congruent, we call it isosceles. And then that immediately establishes something called a base. Because two sides are the same, we now have something we call the base, and the other two we refer to as the leg. So it has congruent legs, and then the third side is the base. So when I talk about an isosceles triangle, I will reference the base several times because we need to understand that the base, being the bottom, is where we're going to have some congruent angles. And that comes from our theorem, and it says that if two sides are congruent, then the base angles are congruent. So if you look at our picture right here, I notice that I have two sides that have been marked as congruent, and that makes these two angles down at what we call the base to be congruent. Okay, that's a pretty important theorem to work with because we're going to use that a lot in solving problems or applications that have to do with isosceles triangles. And if you think about looking at it overall, it looks very familiar. Most everybody, if you have, on your house, probably has an isosceles triangle forming a roof. So something that we see a lot when we go out into the real world. So we'll look at this first example, and we're supposed to, and I didn't write it down, but we're going to solve for x. So our goal is to solve for x, and we'll figure out that angle while we do it. So solving for x. All right, well, first thing I want to notice about this problem is I'm going to be utilizing previous lessons to do it, but the first thing I need to notice about it is that I have a set of congruent sides on the left and the right, establishing that to be an isosceles triangle. And if I think about the theorem, if two sides of the triangle are congruent, then the base angles are congruent. So that means that right away I can go ahead and pencil in that I now know this is 30 degrees. Now, the theorem I would use for figuring this out, I have two different ways I can go. I can use the theorem that we learned earlier about triangles being that all triangles, the interior angles of all triangles add up to 180, and I can jump right in with that. So I'm going to probably go with that route, and I'll show you the alternative route in a moment. But here's what I know. All of these angles have to add up to 180. So if I make this into an algebraic equation, 30 plus 30 plus 5x plus 15, I know that this all has to equal 180. So 30, let's combine our like terms. I have 30 and 30, which is 60. And then I have a 15. That makes 75 plus 5x equals 180. All right, so now I'll get into that. If I want to solve it, I could take 75 from both sides. And I've got 5x equals 105. If I divide by 5, x ends up being 21. So I know that x is equal to the number 21. And I also should be able to recognize that I know that triangles make 180. So if this is 30 and this is 30, that's 60, which means this top angle had to be 120. Because when I plug them all in, I should come up to 180. And if I plug in or substitute 21 back into that, 5 times 21 is 105, and 105 plus 15 makes 120. So that is how I use base angles and the isosceles triangle theorem to solve a problem. All right, let's do the same one. Please understand that just because I turn the triangle sideways does not mean that the base is all of a sudden a different base. It's the same base. This is our base. It's just been turned sideways, which means these two are congruent. Although not actually used in this problem, they are congruent. In this problem, I need to solve for x. And I'm going to go ahead and figure out all the different sides. So when I look at this problem though, what is the two things that I can write algebraically? What's the statement I can put together algebraically? When I look at this picture, I have 3 different items, but 2 of those items are equal. And it's because these marks tell me this is an isosceles, and that should tell me that this side this leg should be equal to this leg. So I can write that out like this. Now this leaves me with variables on both sides of the equation, and being a math teacher, I want to make sure I go back over my algebra. If I have 8x's on the left side of the equation and 4 on the right, I normally want to cancel the smaller of the two. So if I take 4x, that leaves me with 4x minus 1 equals 5. All right, so if I add 1 to both sides, I get 6. So 4x equals 6. Well, dividing by 4, that makes x equal to 1.5. Not the best thing I want to work with, but it's totally doable because we always have a calculator and we can just plug that number back in, substitute. If x is equal to 1.5, yeah, we prefer not to have a decimal, but we can work it out. So we just plug it in each place. 2 times 1.5 is 3. 3 plus 11 makes 14. However, let's look at the two that we know to be equal. All right, 4 times 1.5, let's see, 2 times 1.5 was 3, so 4 times 1.5 would be 6, and that makes this one 11. Because 4 times 1.5 is 6, and 6 plus 5 is 11, and then what do we automatically know about this one? Since it's isosceles, without doing any math, I know that this one is equal to 11. And that's how the theorem works for isosceles triangles. Now we're going to look at the second one called an equilateral. Equilateral triangles. If 3 sides of a triangle are congruent, then all the angles are congruent. So we call them equilateral triangles, but in reality they're actually equilateral and they're called equiangular. So right away I know that all angles are the same. So I know that these are all the same, but I also know exactly what number they are, because triangles always have to add up to 180, and if you have 3 of the same item, that means that these are all 60. Which tells me right away how to jump right into this problem, because when I know that they're all 60, I can fill in every blank on this triangle without actually having any numbers to start. So here's how I do it. First thing I notice is that I have 1, 2, 3 the same. They are all the same, which means all the angles are the same. So I can go ahead and erase all of these and just start writing in the numbers. I know that they're all 60. Now, if I go back to chapter 1 when we learned about linear pairs, I see that this angle and this angle are adjacent to each other. They form a straight line, so they're called a linear pair, which tells me that this number and this number have to add to 180. So this has to be 120. Now I also notice that these two sides are the exact same length, which means that this triangle off to my right is an isosceles triangle. Although this is the base, it's kind of upside down, it's an isosceles triangle. And isosceles triangles have 2 sides the same, and I see that this top angle is 180, so these base angles have to be the same number. Well, triangles make 180, so 180 minus 120 gives me 60, which means that each of these has to be 30. And that's how I use the equilateral triangles theorem to solve a problem. And my very last example I just want to go over is something for solving length. In this diagram, I see that all 3 sides are equal. And it asks me, it says, what is the height of triangle ABC if BC is 12? Well, if this is 12, I know that this is 12, this is 12, and this is 12, but they're asking me for the height. I want to know this. How tall, what is the height? However you want to call it, how tall, how high, what's the altitude? Regardless, I want to know, and that's a terrible line, I want to know this distance. Well, I can do that if I go back to chapter 1 again and we look at something called the Pythagorean theorem, because I know that if this and this, if I divide this right down the middle, I make a right triangle. which means that if this is 12, this is 12, this is 12, I could maybe rewrite this to go 6 and 6, because 6 plus 6 is 12. If I make a little right triangle out of it, I can use the Pythagorean theorem and go 6 squared plus h squared is equal to 12 squared. So 36 plus h squared is 144. So I've got to take that. Looks like I got to do a little subtraction. So 144 minus 36 leaves me with 108. And how do I undo a square? Well, I take a square root. So if I take 108 and I find the square root, I get that it is 10.39 approximately. So our book normally uses tenth. So I'm going to say approximately 10.4 is the height. And that concludes this lesson. I just hope that this answers a lot of questions for you and it gives you good advice on how to get this done. All right, thank you. Bye.